we will introduce quantifiers. What are quantifiers? Those are simply just the words refer to quantities, like including this, some, all. Now, the two quantifiers that we are going to introduce, this one means all, for every element. And this one, we read that as exist. So that means for some, there is at least one. So these are the two. And again, this is read for all. This is read there exists. Two another symbols that we need to introduce because we'll use them so often. The first one is this one. It represents such that. Okay, such that you just write it like that. And the second one is this guy. This guy means in or included. For example, one is included in this set. One is one element of this set. So we can write one is included in this set, or we just simply say one is in this set. To type these symbols, like these four symbols, in a word math equation format or in a LaTeX, to type this one, it's \ni, and this one is in \in. Probably this is just the backwards of in, so probably that's why we the syntax is just \ni instead of in. To type this symbol is just \for all, so it literally represents what this symbol means, and this is \exist. All right. Again, this symbol for all means for all, for every, for arbitrary, for any, for each, given any. So they all share the similar meanings, basically for all. When this symbol is used, we have a universal statement. So a universal statement is in this form: for all x in the domain D, a set D, usually it's the domain, Q of x. So this is a predicate. Q of x will be true. So for all x in D, Q of x is true. Now, when is such universal statement is true? Because this is for all x in D. That means when Q of x is true for all elements in this set D. So in other words, when is this universal statement true? If you check all the elements in X, all the elements X in this set D, this Q of X is always true, then this whole statement is considered true. Now, when is it false? That means when there's some element X, at least one element X in D, so that Q of X is no longer true, which violates this for all quantifier meaning, then this statement is considered false. So if there is one A value, okay, as long as you can find A value, one value, X, such that Q of X is false, then you can say this universal statement is false. Now let's take a look at a couple of examples. Say, suppose let D be the all students currently in Info 2030. Consider the statement, for all X in D, X is at least 17 years old. So here's the predicates, because there's a variable here. So this is a predicate. How would you show this universal statement true or false? And just so pause the video for a moment and think about, so consider this sets D, all students currently in this info 2030, and this, consider this statement. How do you verify this is true or false? Now, how do we verify that? You have to go through each student in this class. Say, suppose we have A, B, C, D, E. Say, suppose, say Allison, Ben, Carlton, Dalton, and Eddie, for instance, these 5 people. Then we are going to look at them each one by one. Is Allison at least 70 years old? If it is, then we go to the next one. Is Ben at least 70 years old? And so on and so forth, right? If all are true, if we check all students, they are all at least 17 years old, then we are going to say this statement is true. Now, if someone happens to be less than 17 years old, then we are going to say this statement is false. So this method involves checking every element in this set D, whether the elements will make these predicates true or false. So we have to check every element. So this method is called the method of exhaustion. So exhaustion, okay? Method of exhaustion. So basically you check everything. So this is one way to prove that a statement is true or false, the method of exhaustion. Now let's take a look at the second example. For all x in R, R means real number. So for any real number, x is greater than 1 over x. So is that true or false? So again, I would encourage you to pause for a moment and think about it. So some of you may try, okay, for all x in R, so I'm going to try some x in R, some real numbers. Say, suppose you try 2x, let x be 2. So is x greater than 1 over x? So you see 2 is 2 greater than 1 over x, 1 over 2? Yes, you're going to say this is true. Now, does that mean it's true? Well, this is a universal statement. In order for you to conclude this universal statement is true, you have to consider all elements in this set, in this case, real numbers, right? And I hope that you realize that there's no way you can check all real numbers to see if this is true, right? There are many, that's true, it's unrealistic. Now, actually, this one, if you try a few more, say, let's check x equals 1, right? And 1 greater than 1/2, 1 over 1, because x is 1. X is 1, 1 over 1 is 1. Is this true? Is 1 greater than 1? This is false because 1 is equal to 1. 1 is not greater than 1. So in this case, is this statement true? It's not true because we are not all x in R, so that x is greater than 1 over x. We already found a so-called counter example, or one example that contradicts to this statement, right? So in this case, how would you show a universal statement is false? You're gonna just find a counter example. So we are gonna call this as counter example. Okay, so this is how you should show a universal statement is false. So just find that. Just find just one value. The next universal quantifier is the exist. That means there is a element, or we can find a element, or there is at least one element, or for some, or for at least one. They all meaning that they exist. And when the exist is involved in a statement, we call that as an existential statement. That's quite intuitive. And oftentimes it is in this form. There exists x in a set D. And if you remember, this means such that Q of x, such that Q of x. Now, when I say true, because this says there exists one, right? There exists one. So if you can find one value x in D so that Q of x is true, then that means this statement is true. So we're going to say when Q of x is true for as long as you find one, so at least one value x, then you can consider this existential statement true. When is it false? That means you cannot even find one value of x in D, so that this is true, right? So in other words, when Q of x is false, because you cannot find any one value in D, so that this is true. That means it is false for all values. For all values of x. This is how you show an existential statement to be false. Let's take a look at this example. Let's prove or disprove. First of all, you have to determine whether it is true or false. So this means there exists m in z. Z means integer, so that means there exists an integer such that m squared is equal to m plus 2. So now give it a try. Are you able to find one integer whose square is equal to the sum of this integer plus 2? Okay, so again, let me quickly write this down. This means there exists, right? There exists an integer. The integer means it's coming from the z, and such that m squared is equal to m plus 2. I hope that you see that math is really a different language. It really translates into English like in this sentence. All right, so I think it would not be too hard to find that when m is 2, we can see that n squared is equal to 2 squared, which is 4, right? And this is this side, your left-hand side. This is your left-hand side, by the way. I'm going to write this left-hand side. And take a look at the right-hand side. Right-hand side is m plus 2, which is 2 plus 2, which is 4. Do you see that we can conclude that, like combine these two, we can conclude that left-hand side is equal to the right-hand side. And because we are able to find a integer, so that this is true, and this is an existential statement, and therefore we successfully proved that this statement is true. So we're going to say, therefore, the statement is true.